Yeah, the next talk is compiling and running high-level quantum programs by Hristo.
Hi, I'm Hristo Venev. I'm a PhD student at Insight, and I'm here to talk to you about compiling and running high-level quantum programs. Now, what are high-level quantum programs? Well, and programming languages. They are ones that make it easier to implement, for example, high-level algorithms safely and hopefully without too huge amounts of boilerplate. A recent development in that area is Silq from PODI 2020, which has a linear type system which gives us some safety properties. Because, for example, in quantum computers, you can't just drop qubits and you can't clone qubits. These things are impossible, and the linear type system guarantees that. It also provides automatic uncomputation, which, because of this fact that you can't drop qubits, when you compute something after you're done using it, you have to somehow uncompute it. And in many cases, Silq can synthesize Silq is able to do the uncomputation for you, so you don't have to manually write the code to do it. And finally, Silq is physically realizable. That is, if we have a program which is well formed, then it is physically realizable on a quantum computer. There's, however, a slight problem with that. There is no compiler for Silq or for any of the other high-level quantum languages, but Silq is the most comprehensive one, so that's the one we are focusing on. There are challenges with designing a compiler. For example, high-level programs aren't exactly circuits. They can have control flow, they can have functions, they can have higher-order functions, they can have uncomputation and many other things which don't trivially map to gates. And they aren't classical either. We can't just run it on a classical computer. We obviously need a quantum computer. So we kind of do need to get something to a quantum circuit-like state. And we need non-trivial program transformations to, for example, synthesize uncomputation, which, we will see how we can do it. And finally, if we want it to be convenient to write high-level algorithms, we want compiler optimizations, because hand optimizing code isn't really a nice experience, especially when implementing high-level algorithms. So basically, having a compiler for such languages would enable broader adoption of quantum programming. So let's look at the intermediate representation we use for our compiler and what our goals are and what constraints those goals imply. We must support Silq, therefore we must support all the features of Silq. In this talk, we will focus on automatic uncomputation, quantum conditionals, which is if statements where the condition is a qubit, which we don't measure, and instead it's like a coherent execution of the if statement. And we will take a look at loops as well. And of course, as we want our IR to be used for compiling the program to something that can actually run, we must make sure that our IR is physically realizable as well. There are representations of quantum programs which are useful for program analysis and for static analysis, but aren't physically realizable. So we want something that is realizable. That's why we designed HQIR, which is a graph intermediate representation with value nodes and operation nodes. It's somewhat similar to the value dependence graph introduced in POPL'24, but there are some differences. Because of the linear type system of Silq and the fact that weakening isn't allowed, we have move edges, which move the values, and const edges, which are just for operations which borrow values but don't actually consume them. For example, here we have a program that, given two borrowed integers x and y, and a moved integer z, computes z plus x times y and returns z, where it consumed the original one and returns the sum. The way that is implemented, that would look in the IR, is we take x and y, we give them to multiplication, which doesn't consume its inputs. Instead, it just borrows them because multiplication isn't reversible. So yes, I forgot to mention that all quantum gates are reversible. So we must always be able to reverse any operation that so when we have its outputs and its borrowed inputs, then we must be able to reverse it and get the original consumed inputs back. But so for multiplication, this is impossible. So it has to be like this. And it produces an output which we must then consume. We'll deal with that later. And we have z, which we add to x times y. One of the operands of the addition can be consumed because it's reversible. So the question is, and of course, we have order dependencies between the operations, which are implied by the data dependencies here, plus uses the output of multiply. So we have an order dependency between them. Now, what do we do with this? What do we do with x times y? Well, we uncompute it. We insert a forget node, which must somehow do the right thing. And the right thing is to find how the value it's given is computed. In this case, this multiplication, and apply the adjoint of that operation. So basically, run the circuit in reverse, and this thing will consume the output of the multiplication, and will not give us anything back, because that's exactly the opposite of what the regular multiplication does. This is only sound when we know that the input is exactly the one that would have been given by the multiplication. So if we have something else here, but we do the reverse of multiplication, then we will get a program that doesn't behave in any reasonable way. The Silq compiler guarantees that uncomputation is possible, and because we synthesize forget by going back through the value dependence graph to find how the value was computed, then we must also then we also do the correct kind of uncomputation. Dependencies are also a bit interesting. Here we have again we have the dependency from plus to the multiplication. We have a dependency that forget must happen after the multiplication, but because forget consumes x times y and plus borrows it, then we must also have a dependency which says that the addition must happen after the forget. The exact same dependencies are present after the uncomputation has been made explicit. This transformation is necessary if you want to run the program on a quantum computer, because we can't give forget to a quantum computer, but we can give it a circuit. So far, we've only looked at straight line code, which is a bit trivial. So let's see how we will deal with if statements. Well, the idea is that we have controlled nodes, which can be turned on and off based on a condition that's stored in a qubit. And the way we deal with values is using the split and merge operations. Split takes an input and a predicate and produces two outputs which only exist conditionally. One output exists if the predicate is true, and the other one exists if the predicate is false. Then we can pass these condition registers, these values that exist conditionally, to controlled gates, which only happen if the condition is true, in which case this Adamar gate depends on x. And finally, we perform a merge operation on these conditionally existing values, which has the same predicate. And we get a value that doesn't have any conditions related to this value x. For a valid intermediate representation, it must be the case that all values are consumed exactly once, in the sense that they literally have one edge that's going out of them, that's a move edge. And the conditions must perfectly match. So you can't have two edges out of the same value with different conditions. You have to explicitly use split and merge. And by having split and merge depend on the predicate, we also ensure that this can be physically realized. This also includes the dependencies, because this is just a borrow, like a const edge. On the right, we have a different example where we use a select node instead of a merge node. The difference is that a select node borrows its inputs instead of consuming them, which means that, well, it doesn't consume them, so they must be consumed somewhere. And it also produces a value that must somehow be uncomputed, which we do with forget at the end. This function here, you can see, just computes a truncated difference by first comparing, doing a select to which matches the if statement, and doing a subtraction on the output. If we look at the dependencies, we can see that the forgets must happen after the subtraction. And finally, maybe the biggest challenge so far is how do we do loops? It turns out quantum computers don't actually do loops natively. You just have to give them a sequence of gates. So what's done in low-level IRs is loop unrolling, but that limits you to loops with a fixed bound. And Silq doesn't have this restriction, so we must be able to support arbitrary loop bounds, as long as they are classically computable at some point during the execution of the program, which may depend on measurements, etc. So unrolling is not an option for our intermediate representation. It's also not great because it prevents loop optimizations, and you have to apply the same optimization over and over at each iteration, which is bad for compile times. So how do we not unroll loops? Well, we do something that's slightly different from what's done in value dependence graphs. We represent the loops symbolically using indexed nodes. So here this f and this forget, the forget is implicit in the program, are given indices based on which iteration we are in. And this loop node is another operation of the IR that moves the values around correctly based on which iteration we are on. So we have the original input. Oh, this should be a solid line. We have it being given to f, which f doesn't consume it, and it being forgotten. And then we give the output of f to the next loop iteration. Here's an interesting thing. If we look at the dependencies, it turns out that we must first do all of the f's sequentially, like from 0 to n, and only then we must do all the forgets in reverse order. So we also have dependency edges which are expressed symbolically. For example, fi has to happen after fi minus 1, but forget I must happen after forget I plus 1. So this is an interesting challenge that we believe we're the first ones to solve, at least in this way. In conclusion, we've presented an IR. We've shown what the design considerations were. We must be able to support Silq. In this presentation, we only focused on certain features of Silq, but other features are also supported. Well, we aim to support the entire language. In particular, we didn't cover measurements. We didn't cover classical computation, and there are other things like higher order functions and dependent types and so on, which are mostly handled at the front-end level. Then we saw the base version of our high-level quantum intermediate representation for straight-line programs. We saw how we can do uncomputation in it. We saw how we can extend it with support for conditional operations using control edges and split, merge, and select operations. And finally, we saw how we can implement loops using indexed nodes. And I believe that by having a compiler that implements these things and being able to support high-level quantum languages, we will enable broader adoption of quantum programming. Do you have any questions?
One key questions.
So you mentioned your index nodes to represent loops.
Yes.
Could you comment on how that might compare to a polyhedral intermediate representation in a regular compiler?
Yes, this is interesting. It is somewhat similar. But so in the case where you know all the loop bounds in advance, it is exactly a polyhedral representation. But sometimes you actually get the loop sizes in the middle of the computation. So maybe you have a nested loop, and you get the inner iteration count in the body of the outer loop at each iteration. So that's not exactly a polyhedron. It's possible that you have a while loop, in which case you actually don't yet know if you're at the last iteration or not. And it might be the case that you need to do a measurement on a qubit. This might happen during state preparation, for example. Let's say you want to pick something that's in a uniform superposition of being 0, 1, or 2. Well, you pick something that's in a uniform superposition of 0, 1, 2, 3. You check if it's equal to 3, you measure that. And if it's false, you're done. If it's true, you need to repeat. And you throw it out and you generate a new number and so on. So it's, so in the case where you do know the loop bound in advance, you can use polyhedral, all the work on polyhedral optimization.
Thank you.
Any other, or do we have time for more questions, or?
I think we should finish here. And the winners will be announced during the business meeting. So please don't miss the business meeting so that we can hear about the results. And thank you for the last talk as well. And that concludes the SRC presentation session. Thank you so much.